Welcome to our exploration of wave mechanics. Today, we are diving into the Doppler effect. You have likely experienced this when an ambulance passes you. The siren sounds high-pitched as it approaches, then suddenly drops in pitch as it speeds away. This is an apparent change in the frequency of the wave, caused entirely by the relative motion between the source emitting the wave and the observer receiving it. Crucially, the source's actual emitted frequency never changes, only how it is perceived changes. To analyze this mathematically, we must establish our variables. We distinguish between the true properties of the wave as emitted at the source, denoted by f for frequency and lambda for wavelength, and the apparent properties detected by the observer, labeled FO and lambda sub a. We also define v as the wave's propagation speed through the medium, while us and uo represent the physical velocities of the source and observer, respectively. Let's first look at the simplest scenario, when there is absolutely no relative motion. Here, both the source and the observer are completely at rest, meaning both Vs and Vo are zero. Because there is no motion to distort the wavefronts, the observer detects the waves exactly as they are emitted. The true frequency f is simply the wave velocity v divided by the true wavelength lambda, and the apparent frequency equals the true frequency.
Now let's introduce motion. Consider what happens when the source moves toward a stationary observer. As the source travels forward, it partially catches up to its own waves, compressing the wavelength in front of it. This shorter apparent wavelength, lambda sub a, is calculated as v minus us divided by the true frequency. Because the waves are bunched closer together, they strike the observer's ear more frequently, resulting in an apparent frequency, FO, that is higher than the true emitted frequency.
Continuing our exploration of the Doppler effect, let's now look at what happens when the source moves away from an observer who remains at rest. As the source retreats, it pulls away from the wave crusts it has already emitted, stretching the apparent wavelength. Because the wavelength increases, the observer receives fewer wave crusts per second. This results in a lower apparent frequency, which explains why a siren's pitch drops as it speeds away from you. Now, let's shift our perspective to case 2, where the source is stationary but the observer is in motion. In this scenario, the physical wavelength of the waves in the medium does not change. Instead, the observer's motion alters the relative velocity of the waves they encounter. When the observer moves toward the source, they intercept wave crests more rapidly, effectively increasing the relative wave speed to v plus u0, which drives up the apparent frequency. Conversely, if the observer is moving away from the stationary source, they are traveling in the same direction as the wave propagation. This means the waves must chase down the observer, reducing the relative wave speed to v minus u0. Because the relative velocity decreases while the wavelength remains unchanged, the observer detects a lower apparent frequency, hearing a lower pitch or seeing a redshifted wave. What happens when both the source and the observer are moving? In this case, both the wave velocity relative to the observer and the physical wavelength are affected. When they approach each other, the relative wave speed increases to v plus u0, while the wavelength is compressed to v minus us over f. Combining these effects gives us a significantly higher apparent frequency, as both motions work together to compress the wave cycles. When the source and observer are moving away from each other, we see the opposite effect. The relative wave velocity decreases because the observer is fleeing the waves, represented by v minus u0. Simultaneously, the moving source stretches the wavelength to v plus us over f. This dual expansion results in a much lower apparent frequency, as the wave crests are both stretched out and chased down. We can also analyze mixed scenarios. Consider a source approaching an observer who is moving away. Here, the source's forward motion compresses the wavelength, which tends to increase the frequency. However, the observer's retreat decreases the relative wave velocity, which tends to lower it. The final apparent frequency depends on which speed is greater. If the observer is moving faster than the source, the overall frequency will decrease. Similarly, if the observer is approaching while the source is receding, we have another competing situation. The observer's motion increases the relative wave speed, raising the frequency, while the source's retreat stretches the wavelength, lowering it. The resulting frequency is determined by the ratio of v plus u0 to v plus us. This demonstrates how the Doppler formula dynamically adjusts to any combination of velocities. By synthesizing all these cases, we arrive at the general Doppler equation, which elegantly handles any relative motion. This powerful concept isn't just theoretical, it has vital real-world applications. It's used in radar speed guns to catch speeding cars, in astrophysics to measure the rotation of stars and detect binary systems, and even by bats utilizing echolocation to navigate. Next, we will dive deeper into how these applications work in practice. Let's examine how a radar speed gun measures a vehicle speed using a double Doppler shift. First, the stationary radar gun acts as a transmitter, emitting microwaves toward the approaching car. Because the car is moving toward the source, it observes a higher frequency, FA. Then, the car reflects these waves back toward the radar gun. In this second phase, the moving car acts as a moving source, and the stationary radar gun acts as the observer, receiving an even higher shifted frequency, FA prime. By analyzing the difference between the emitted and reflected frequencies, we can calculate the car's exact speed. The fractional change in frequency simplifies to 2u over c minus u. Since the speed of light, c, is vastly greater than any car speed, u, we can approximate c minus u as simply c. This gives us an elegant, direct relationship. The car speed, u, is equal to the speed of light times the beat frequency divided by twice the original frequency. We can also use the Doppler effect to measure the extreme temperatures of nuclear fusion plasmas. In a hot plasma, atoms move rapidly and randomly in all directions. Those moving toward us shift their emitted light to shorter wavelengths, while those moving away shift to longer wavelengths. This creates a broadening of the spectral lines. By measuring this wavelength spread, delta lambda, and applying kinetic theory, we can calculate the absolute temperature of the plasma. Astronomers determine how fast stars are moving relative to Earth by analyzing their light spectra. If a star is moving away from us, its spectral lines shift toward longer, redder wavelengths, a phenomenon known as redshift. If it is moving toward us, we observe a blue shift. By comparing the shifted wavelengths in a star's photograph to a stationary reference, we use the formula U equals c times delta lambda over lambda to calculate the star's precise radial velocity. The Doppler effect is also highly practical in biology and medicine. Bats utilize ultrasonic echolocation to navigate and hunt. By emitting high-frequency sound waves and analyzing the timing and frequency shifts of the returning echoes, they instantly judge the distance and speed of obstacles or prey. Similarly, in medicine, doctors use Doppler ultrasound to non-invasively measure the velocity of blood flow and track tissue motion inside the human body. In summary, the Doppler effect is a powerful tool across multiple scientific disciplines. Whether we are measuring the speed of a speeding car on a highway, calculating the temperature of a fusion plasma, tracking the expansion of distant stars, or mapping blood flow in a clinical setting, tracking frequency shifts allows us to perceive and measure motion that would otherwise remain invisible.